Okay, our first presentation for this session is presentation by Eduard Morozov with the title Optimizing Neural Network Loss Function with Differential Evolution. Eduard, you are welcome.
Yeah. So, do you see the presentation?
Yes, we see.
All right. So, I can start?
Yeah, sure.
Okay. Hello, everyone. My name is Eduard Morozov, and I'm glad to present our work is optimizing neural networks loss function with differential evolution. So, the purpose. One second. The purpose of this work is optimizing coefficients of loss function to obtain better accuracy for training neural networks models. In nowadays, neural networks used too widely in different areas of our life, and important aspects of training models is choosing the loss function. It is the function that is responsible to compare the predict value and true label of the model. For these years, we have more different modifications of loss functions, but usually in classification tasks using cross entropy. Cross entropy is a simple loss function, and you have simple form. On left right side of the slide, we can see the formula where x is a true result of true label of our class, and y is the results of predicted by the model or predicted label. So what if we can train models better with different loss function? So we have two ways. First way is trying to use genetic programming and try to grow own function. Second one is using different polynomial. So Santiago Gonzalez and Risto Miklainen tried the both ways and came to the conclusion that using polynomials is better. And they suggested to use the simplified polynomial Taylor expansion on the slide, formula on the slide. So how we can see in this formula, we have 8 coefficients, theta, and we need to find them. How? So to find these coefficients, we use evolutionary algorithms. In our case, differential evolution. Why differential evolution? In latest CEC competitions, as a rule, out of 15 algorithms, near 10 is a differential evolution. So make suggestions. To find coefficient, we use SRDE. This is algorithm success rate differential evolution, which have modification on success rate. So usually in differential evolution, using mutation for population diversity, and in most efficiently way is strategy of mutation is DE current to P best 1, where we have F, the scaling factor parameter. Usually this is constant, but in our algorithm we change it by success rate. It is a squared of number of improved divided on size population. For the algorithm, we can see in pictures on the right side of slide. We initialize the population and calculating the value of fitness function. So value of cross entropy on test data is used as fitness value. So we train the model with a Taylor polynomial, but the value of cross entropy was used as fitness function. After that, we use an operation mutation, crossover, and we have new changed population, which we also need to find our fitness values. And after this, with operation selection, we compare our populations and replace the start population the new more efficient individuals. So this cycle repeats until we make it require number of generations, which is set as a constant before the start of the algorithm. So experimental setup. So 1 second. This proposed algorithm was tested on dataset FAR10. This is object recognition task with colorful images, size 32x32x3. It contains 15,000 of images to train the model and 10,000 images for tests. Also, we use these parameters for our algorithm for neural network. Batch size 100, optimizer is a stochastic gradient descent, and we trained our neural network for 200 epochs. And for evolutionary algorithm, we have population size 15, and lower and upper limit individual of theta is 10 and minus 10, and for 64 generations. Start CR is 0.9 and start F is 0.5. So as a result, we can see the proposed algorithm show us a little bit better results on most architectures by accuracy. And also as a proof of concept, we tried to use a basic differential evolution, but only trained on 225 calculation of object function. So 1 second then. Okay. Why is so small? Because calculation needed amount of computer resources and time, and we tried algorithm which we think better. So for obtain coefficients, we try to plot graph, but use different formula for two classes. How we get it? Probabilities of belonging of two classes, we know the sum of this equals 1. Equals 1. That means that we can express the second class from the first. And let's remember formula of Taylor polynomial. We have sum for classes, and this is have two expressions, sum two expressions of each classes. So using this formula, we can get form of loss function for two classes. And how we can see, the loss function obtained with SRDE have a quite different and poorly interpreted form. But as we can see, the left side of the graph always is upper than right side of the graph. It means a more confident answer is penalized less than a less confident one. And also we can see the function is obtained with DE, most familiar form. It have a minimum at 0.57, and on the right side is going upper. It means the function penalized only confident answer, which reduce overfitting. So also we have distribution of coefficients in process optimizing. We can make a conclusion about few theta must be around 0. For example, it's theta 2 and theta 8. And the rest thetas can be different values to obtain the best accuracy. Also, in the graph, you can see the values below 10% on the graph. This means there was a similar form of loss function, SRD, but perhaps the left side was lower, and the time, therefore, model deliberately did not guess the image in the process optimizing. So that's all what we get, and as a conclusion, the coefficient was optimized, which made it possible to achieve better accuracy compared to cross entropy. But using this algorithm requires a large amount of computer resources and time. And in future, it's planned to use other optimization algorithms, datasets, which with a large number of classes, for example, SFAR 100, as well as the surrogate approach. Thank you for your attention. I'm ready to answer for your question.
Thank you very much for presentation. Dear colleagues, you have possibility to ask a couple of questions.
I have a question. Sorry
Yes.
if I missed it. This equation you have, what is a derivative for this equation? How you can, is it simple derivative like in, for example, cross entropy or other metrics, or you need to use some numerical methods to find derivative?
I don't know what it means, derivative. I forget.
Производная.
Can you repeat this question with understandable? Now I understand this word and I easily to understand your question. Can you repeat this?
I will say it in Russian.
Okay.
Насколько сложно производную от этой функции получить? Потому что от тех, которые стандартные, легко.
In this function, only have O and sum and not very strong, not very hard to obtain derivative, because have only simple operations of math.
Okay, thank you.
Well, thank you very much for your answering, and we will go to another presenter. Our second presentation for now is will be presented by Denis Shabalin with the title Neural Network-Based Vehicle Control in Simulating Environment using Real-Coded Genetic Algorithm. Denis?
Hello, esteemed conference participants. Do you see the slider?
Yes, we see, we hear. You are welcome to start.
You can see contact information on the screen. Large companies are addressing similar challenges. For example, NVIDIA develops a complex AI-based virtual object obstacle course to train robot dogs to walk in minutes. In my life, the method of optimizing neural network using a real code genetic algorithm for the task of controlling a car in simulation environment, consider potential and effectiveness. The aim of the work was to conduct research of the method of optimizing neural network using a real code genetic algorithm for the task of controlling a car in a simulation environment. To achieve this, it was necessary to develop a genetic algorithm, create a simulation environment, conduct experiments with varying parameters, analyze the results, and compare them with the human baseline control. In my work, I use a real coded genetic algorithm, the block diagram of which you can see on the screen. The selection operator used is tournament selection. The crossover operator used is simulated binary crossover. Distribution graph is displayed on the screen. The mutation operator used is power mutation, and the formulas for its computation are shown on the screen. The structure of the neural network in my work is quite simple. Feed-forward network is used with the activation function for all neurons being the hyperbolic tangents. The input layer consists of 3 neurons, what we later receive sensor data. This is followed by 2 hidden layers, and the outward layers has 2 neurons. The first neuron control the steering angle of the car's wheel. The second neuron controls the acceleration force of the car. The neuroevolutionary approach involves encoding weights and biases. Each weight or bias of neural network is encoded into an individual gene and represented as a real number. The neuroevolutionary algorithm is particularly advantageous for optimizing neural networks in scenarios where defining a suitable loss function is ever challenging or impractical. For simulation, the Unity game engine was used. A virtual loop track was created for training the neural network with a width of 7 meters and a total length of 308 meters. The car's position of the track is determined using a formula what calculates the nearest position, the nearest point of the track relative to the car current position. To ensure vehicle control, 3 distance sensors were used to detect the nearest object. Each sensor has a length of 33.3 meters. the entire algorithm scheme is displayed on the screen. The genetic algorithm was written in C++. The neural network was implemented using Unity Scientist library. The rest of the project was written in C#. To optimize the project, it was developed using Unity data-oriented technology stack, and population evolution was conducted in parallel, and one simulation cycle lasted 25 seconds. Five main parameters were during the experiments. Это the crossover spread parameter, notation strange, denoted as P, tournament size denoted as T, population size denoted as N. The performance achieved by a human is defined as one unit with a fitness function. The experiments produced fitness result under different parameters. In the left figure, the best result was achieved with eta 9. In the right figure, notation strange. In the right figure, with parameter eta 9, the best result was achieved with a tournament size of 9. While the tournament size of 3 also show good results. In these figures, mutation strange was worried. In the left figure, mutation strange was set to 1, and in the right figure, mutation strange was reduced to 1.5. The best result was achieved with population size 128, tournament size 3, eta 1, power mutation 0.5. You can see what initially the population is in the first generation and behaves randomly due to a random integration of gains, but later it outperforms the human. It is possible in the future to expand the approach to more complex simulation with diverse environments. The algorithm can surpass human performance, and this is achievable on a regular laptop within an acceptable amount of time. Thank you for your attention. Feel free to ask question.
Dear colleagues, who would like to ask a question?
Sorry, can I? It's
Yeah.
not a question, it's a little bit of remark. I don't know. Is it a good idea to say outperforms a human? Because a lot of questions arises. For example, who is this human which is outperformed by this algorithm? Where did you get this human data? Is it a medium, some average human, or who was it? So how did you do it?
I practice many times to achieve best result, and it's my best result.
Well, this human was you, actually.
Yes, yes.
Okay, thank you.
Yes, another question?
Yes, I have a question. The question is about performance measure. Is it possible to find, for example, the best curve, the best trajectory for your car and estimate quality as error? So you can see that genetic algorithm have found the best solution. Or can you prove that you have found this solution?
I think it's possible, but I don't
Okay,
think.
you have very good solution right now. Can we improve it?
Yes, I think it's many different solutions to improve this performance.
I can't imagine how vehicle will drive on this circle if we improve. It seems it drive exactly in the center of road.
I think
If we will improve, what we can see in the simulation?
Not trajectory. It's not in the middle of the road. It's very complex shape. Many angle.
I also would like to ask question. Could you justify the choice of optimization algorithm for this problem? Why is this one among 12,000 others?
Repeat again, please.
Could you please justify the choice of this algorithm? Exactly this algorithm for this problem.
I'm choose real coded genetic algorithm because it's have real number what best to compute this work.
There are thousands of algorithms which work with real numbers. Why is this one? For example, why you do not use Hook-Jeeves algorithm? For example, an elder mid or quadratic approximation.
Take a second.
Okay, my second question is why you organize experiments in such a, let me say, very old way? Just suggest some variants of operators and investigated all of them instead of 20 years known approach with self-configuration, self-adaptation, instead of choosing variants. Okay, we have no more time. Just remark, it seems so that you choose it first algorithm which was under the hand and then compare this algorithm with your own. Is a really deep scientific research?
This algorithm is very easy to implement with neural network, real code genetic algorithm with neural network. and have good performance.
Algorithm by hook GIFs is much easier to implement. Okay, thank you very much for your presentation, for answering our question. And now we go to the third presenter of our session. It is Nikita Marushkin with presentation topic optimization of regular expressions using competitive coevolutionary algorithm based on symbolic regression. You are welcome.
Good afternoon, dear colleagues. Do you hear me and see the presentation?
Yes,
Thank
we
you.
see, we hear.
Excellent. My name is Nikita Moroshkin, and my academic supervisor is Denis Lilia, and we want to tell you about optimization of regular expression using a competitive coevolutionary algorithm. Nowadays, almost all spheres of human activity are related to data analysis, and despite the development of machine learning models interested in classical algorithms for text data processing remains high. One of the important tasks of text analysis is to search for a substring in for a substring according to a certain pattern, for which regular expressions that define a finite automaton are most often used. There are a large number of regular expression dialects. For example, Python dialects is most popular dialect in programming, or example PCRE or another, which differ in their implementation and their features of realization. To optimize classical regular expression dialects, the finite automaton minimization method is most often used. But existing optimization methods are not always applicable to new syntaxes emerging with the development of low-code platforms and text analytics, which makes regular expression in such cases an abstract black box model. The goal of this research are the development of an algorithm for optimizing regular expression as a black box model, to define an intermediate representation for a regular expression, and to study of competitive coevolution using symbolic regression as an algorithm for regular expression optimization. In which study, symbolic regression was implemented with the gain expression programming algorithm. Proposed algorithm is to use an expression tree based on specific functions and terminals of source regular expression. In general, the problem solved by population algorithm can be represented as to find minimum argument of objective function. And in this case, the individual is in some expression tree. For start, we have some regular expression, and this is a regular expression which we will define as input for our algorithm. For example, the abstract syntax tree is shown on the slide. Then we can define some set of terminal symbols for this regular expression, and for this regular expressions, terminals were A, B, 0, 1, 2, and 3. Then we can also define a set of non-terminal symbols or functions. For example, for this regular expression, the non-terminals were logical OR, quantifier 0 and 1, logical AND, and range function. And then using these functions and terminals of a regular expression, we can construct some expression tree showed on the slide of a given regular expression. The expression tree in this case will be the intermediate state and phenotype of the regular expression for our algorithm. And using this expression tree, we can construct some key expression that will describe the genotype of an individual. Then we need to define the objective function. To evaluate the fitness of an individual in the optimization algorithm, it is proposed to define two quality metrics, such as the accuracy of the regular expression and the efficiency of the regular expression. For this study, the accuracy of some regular expression is classical accuracy metric. And for calculate the efficiency of the regular expression, we will run some regular expression a few times and calculate average time of these runs. Then we need to define the test strings of this regular expression by construction of this expression. And we need to define the function that returns regular expression for the vector x. For example, in this study, it was the expression tree. And the objective function, Q of population regular expression optimizing algorithm, which is used to solve optimization problem, can be represented as this function showed on the slide. And this function has a stub value. Stub is the constant set by the researcher for cases when the obtained regular expression has accuracy equal to 0. This value is not taken into account when calculating statistics, and the regular expression has stub value. Then this is regular expression is not to be able to compile in some regular expression. The coevolution algorithm is proposed to be implemented as a competitive coevolution based on the comparison of individual algorithms by the quality of each iteration. The main parameters of this algorithm were the common resource or shared resource, the length of adaptation interval, the size of social cards, it is the percentage of initial population size, and the penalty of for the losing population. The quality of each population can be determined by the following formula shown on the slide. And this formula, this quality of iterations calculates only after adaptation interval. And the pseudocode of this algorithm shown on the slide. And let's to start with experiments. The proposed regular expression optimizing algorithm was tested using the Python programming language in the PyCharm IDE. The experiments were performed on a computer with the following specifications shown on the slide. And to evaluate the efficiency of the proposed coevolutionary algorithm, the test regular expression was formed, shown on the slide. The constant, the number of times, the number of runs for each regular expression was 100. And in each experiments, in addition to running coevolution, each individual again expression programming algorithm was run separately. The launch parameters for again expression programming algorithm are shown on the slide in table 1, the first table, and in second table shows the launch parameters for the coevolutionary algorithm. I show you to show results, and for a better understanding of the convergence of the algorithms to the minimum Q or objective function minimum, it is useful to consider the values closer to the minimum of objective function value. Let delta 1 is difference between maximum of objective function and the minimum objective function or percentage, and delta 2, delta second. The following intervals can be defined, and these intervals are shown in the figures by filling them with blue and pink colors. And it is advisable to estimate the number of individuals whose values will fall within the above mentioned intervals. And table 3 shows the values of these experimental values for individual algorithms and algorithm launching coevolution and separately. And by analyzing the graphs in table 3, it can be seen that the algorithms launching coevolution were able to obtain the minimum objective function value before the common resource were finish only in one case. Having analyzed the best smaller values of the fitness function or objective function, it can be concluded that the smallest solution for all four experiments was obtained by launching individual gain expression programming algorithm. It should be noted that with an increase in the shared resource, the coevolutionary algorithms may be superior in finding the minimum compared to individual algorithms. As a result of comparing a minimum of objective function with all values for each algorithm, it is easy to see that the coevolutionary algorithm is better than the worst of the individual algorithms, and even better than average algorithm, but not always better than the best of algorithms. The main results of the research that in presented work, a regular optimization algorithm was carried out using a coevolutionary optimization algorithm based on the gain expression programming algorithm. Analysis of the results show that the coevolutionary algorithm is capable of solving the regular expression optimization problem faster than it can be done by running individual algorithms. And the future research is planned to be related to the optimization of regular expression using some rules, equivalent replacement of constructions, testing overpopulation algorithms or population strategy, for example, cooperative coevolutionary, as well as testing over coevolution schemes. In addition, it's planned to study the possibility of treating individuals that are not able to compile into regular expression with the aim of forming a population only from viable individuals. And of course, the future work, we want to study with tuning of parameters of our algorithm. And thank you for your attention. It's all.
Thank you very much for your presentation. Dear colleagues, you may ask a question. Well, let me start. What kind of algorithms did you include in coevolution?
Only gain expression programming algorithm, and implemented with the GAPI framework in Python, which based on deep framework.
Why?
It's too easy to work with tree implementation, for example, which with expression tree. And parallel works, we work with classical population algorithms, for example, differential evolution, particle swarm optimization, and other. And in our studies, the tree implementation is the best for optimization of black box regular expression. And then we use this gain expression programming. And this work is the first work and first try to define the optimization algorithm with three implemented states for regular expressions.
Okay, thank you. Colleagues, any question? Well, there are no more questions. Thank you very much for your presentation.
Thank you.
Answering the question. And dear colleagues, we should start our presentation by Nikita Marushchenko with the title Development of Fuzzy Rule-Based Design Algorithm using a Genetic Algorithm and Inverted Pendulum.
Good evening, that's me.
Yeah, you're welcome.
Give me a second, I will share my screen. Okay, can you see my screen?
Yes, we can.
Okay. I present a work about development fuzzy rule-based algorithm using a genetic algorithm and inverted pendulum model. The goal of this work was to create a program which would create a fuzzy rules base and find input and output terms for this fuzzy control module using a genetic algorithm. The idea behind this work was to create a program which would be uploaded in the programmable controller, which would later learn itself by doing these things. On this slide, the inverted pendulum model is shown. It's a complex model often used in the control and stabilization tasks. The goal of this model is to keep a rotatable pendulum arm in a vertical upright position by rotating the base to which the pendulum arm is connected via a rotatable coupling. The model itself of the pendulum was done in C++, and these graphs show how it oscillates without stabilization. On the group on the left, it is shown that the model over some period of time stops its oscillations. On the group of graphs on the right, the precise nature of the oscillation process is shown. On this slide, after finishing the model simulation, I made a module which implements fuzzy control. And using found manually fuzzy rules and output terms, I tested how this model stabilizes how the system stabilizes the pendulum. It can be seen that on the left side, on the left group of graphs, that after some time, the model was able to stabilize itself. It was able to stabilize the arm in an upright position, but the base wasn't able to stabilize itself because it wasn't the target. Stabilized model is shown with orange lines, and the one which doesn't have stabilizer in itself shown in black lines. Then to connect the genetic algorithm and the fuzzy logic module, I need to decode chromosomes from the genetic algorithm into fuzzy rules and output terms. On this slide on the left, I have the logic behind chromosome decoder. And on the right part of the screen, I have the logic too. On the right side, on the left side, it is shown how input terms of the fuzzy module are decoded in the chromosome, output terms and rules. It uses the same principle as used in the decoding of binary digits. On this slide, it is shown how chromosome precision influences the quality of the model. It can be seen that on the left side, that when I use 10 bits per point, and by point I mean a point of one fuzzy rule triangle. I mean triangles in input and output terms of a fuzzy control. Can be seen that the precision of 10 bits per point is not good enough to stabilize the model using encoded manually found rules, which were the best at this point, because at this point the program wasn't finding rules itself yet. On this slide, on the left, the whole logic of the algorithm is shown. It has functions of the genetic algorithm, like chromosome selection, genetic operations, new population generation, and also it has some functions of the fuzzy logic module, like calculating fuzzy influence. It means calculating stabilization power. And on the right side of the screen, this is the graphs of the first experiments which were done to find the model which would stabilize that pendulum arm position from the starting position of 0.2p. It can be seen on the middle graph that the model oscillates. It starts on like 0.3p value. It means that the pendulum is rotated maybe 20 degrees from the upright position, and it stabilizes itself, but still fluctuates in the middle. The graph on the upper graph, which has the title of base angle, shows that the base of the model still rotates, because this model on the right wasn't using the base angle as the input for fuzzy module yet. Then to have the system stabilized by both the base and the arm, I had to come up with a fitness function. And I came up with a fitness function which is defined by a base angle, an arm angle, a base speed, and iteration number. I also have weight coefficients for each variable inside this function. Then I have made a lot of experiments. And all these experiments can be grouped together in the 3 separate groups. These groups, they all have the same population and generation parameters. This is shown on the screen at the bottom, but they are different if in weight coefficients for each parameter. For example, a graph on the left has arm angle stabilized, but the base angle can be seen that it rotates. The base in this case rotates in one direction. It just spins and spins and spins, but the arm is stable, because in this case the weight coefficient for fitness function was the base has not enough of it. The weight of error it has not good enough weight coefficient. The graph in the middle shows that the base was able to stabilize itself, but the angle had not good enough weight coefficient, so the arm wasn't stabilized. And the graph on the right side of the screen show that the base and the arm both were stabilized. That means that the weight coefficients in this case were the one I need to work with. Then on this slide, I have experiments for vertical stabilization from the rest position. Rest position means a position for the pendulum arm, which is the bottom position. It is the bottom position. It can be, so the target is 0 or 2p, it means vertical position, and the rest position it's the bottom position. It's the position which pendulum reaches when it's not stabilized. So this program was able to find such fuzzy rules which allow the system to rotate itself by swinging in the left and in the right. It can be seen on the group. It can be seen on the graph which has the title arm angle on the left, that the angle stays the same, then it starts to change to fluctuate from the minus 2 minus p. And then at some point, it rotates and stays in the position near the 0 value. On the right, I have a graph which shows the same model, but it has different initial position. The initial position for the group of graphs on the right, on the left is 0, but the initial position for the group of the rights on the right is 0.25p. This slide represents the model with different target position. Models before were trying to stabilize the arm vertically, but this model stabilizes the arm in the oscillations in the oscillation process. This model, unfortunately, only stabilizes the model by its amplitude, but not oscillation, by only an amplitude, but not, it doesn't count frequency of the oscillations. It can be by using a complex fitness function. The model can also find such rules which would reach the target frequency. On this slide, it is shown how they found fuzzy rule base and found fuzzy terms, how the program outputs them. The table on the left means that, for example, rule 10 says that if input 2, it means input 1, base angle. So if base angle is into input terms 2 is used for base angle, and also in B means that input term for arm angle is 4, because rule 10 says 2 and 4 and output is 2. It means that the program uses output term 2. The output terms are shown on the image at the bottom on the right. It can be seen, this model which shown on the screen is the one which stabilizes the arm and the base vertically. So it can be seen on the images that the program finds such input terms which places the most of input terms near the 0 or 2p areas, and output terms the program finds such output terms that they use almost all possible range of values for stabilization power. Conclusion. In conclusion, this work explored and shown the stages of development, such an algorithm for constructing fuzzy rule base and for finding fuzzy rules terms, input and output terms, and demonstrated results of some experiments for stabilizing an inverted pendulum. Thank you for your attention. My presentation is complete.
Thank you very much for your presentation. Dear colleagues, please ask questions.
Yes, I have a question. Can you turn back to previous slide with this one with pictures with triangles?
Okay.
Yes. For me, it seems, for example, for first input term A, you can use only two fuzzy sets, one on the left side and one on the right side, because the difference in support of these terms is not very different. How do you think? Can you simplify the rule base?
Yes, of course, I can simplify the rule base. It's just originally the whole program was using only one input. It was only using the input of the arm. And after doing a lot of experiments, I found not I found, it was visible that the whole program wasn't stabilizing the base. But the reason behind why the amount of input terms and the A and input is just something from making the program itself. It wasn't really because of some reason. It's just that was 6 and that became 6 too. Yes, sure, it can be simplified.
Okay. I think you can check for sensitivity for these terms. And one more, maybe it's not a question, but suggestion, not to use triangle terms, but use some smooth function. For example, Gaussian function. First of all, it's much easier to code into chromosome because you only need to put center and standard deviation. And maybe it will be okay. You need to carry out some experiments to prove if performance become better or will be the same. Thank you very much.
Thank you.
I also have question, but such a, let me say, okay, what new did you do in this area with this algorithm, with this approach, relatively predecessors?
The original, I built this work using some data from the previous work, not mine. It had
Okay, let me reformulate. It's a very old problem, known many years. Approach with automatically generation fuzzy controller is a very old problem statement. Yeah, and development with evolutionary approach and other such kind of approach is very old. What new relatively this very old results did you do?
well, I found work while doing this program that we're doing almost the same, but it wasn't finding input and output terms automatically like my work does. It was only finding the fuzzy table using genetic algorithm, and that was it. But my work, it implemented a method to find also terms. And it was just what I found.
That's enough. I will not agree, of course. Nevertheless, thank you very much. Time is out. Thank you for your presentation and answered questions. And dear colleagues, our session is finished now, and you are welcome to come tomorrow for continuation of our workshop. You are free to go.